Welcome back, everybody. The first talk this morning is by Ferko, who's going to speak about solids and surfaces and geometry of interval deformation for CPN-1 model.
Great, thank you very much. And I'll join the other speakers in thanking the organizers for inviting me to this very nice workshop. It's my first IDD and my first time in Sweden. Sweden seems like a socialist utopia, so I've enjoyed being here very much so far. So first, I just want to contextualize this recent work with my collaborators Michele Galli, Zejun Huang, and Gabriele Tartino-Mazzucchelli, and set it within the context of this workshop. Unfortunately, that's very easy for this workshop because the themes are right in the name. It's about integrability, duality, and deformations. I'm going to be talking mostly about the first and the third, since I'm speaking about integrable deformations. So deformations in particular of 2D sigma models that preserve integrability. But if you're interested in dualities, I should advertise Daniele's talk, which I think is at 3 p.m. today. And he'll speak about some related work. In part, he'll speak about related work connecting the deformations I'll talk about to non-abelian T-duality. So this audience will be very familiar with the fact that these 2D sigma models and their integrable deformations are interesting, not least of which because they describe worldsheet string theories, which are integrable in several cases. Maybe the canonical example is the principal chiral model, which is relevant for string propagation on targets involving group manifolds like S3. Here, my J plus minus is the Maurer-Cartan form built from the group valued field G. And throughout this talk, I'll almost exclusively use light cone coordinates plus and minus. And again, as people will know, there have been many works studying integrable deformations of this integrable 2D sigma model. For instance, turning on a Wess-Amino term, a Yang-Baxter term, a Yang-Baxter deformation, or a lambda deformation. All of these preserve integrability and are interesting to study. What I'm going to do today is talk about a somewhat different class of deformations, and in particular, I'm going to try to endow them with a geometrical interpretation. So the deformations I'll focus on today are known as auxiliary field deformations. They've been formulated for various classes of 2D sigma models, which I will review. And in particular, I would like to explain how this family of deformations admits two complementary geometrical interpretations. So you can view these deformations either as coupling the undeformed theory to a field-dependent metric, which connects a bit to TT bar and what we heard about yesterday from Masahito, or you can interpret them as transforming in a particular special way, transforming the tangent vectors to something called the soliton surface, which I'll explain. So as I mentioned, point one is in some sense a generalization of metric interpretations for special cases of these auxiliary field deformations. Since the TT bar and root TT bar deformations sit within this class, they're particular special cases of this auxiliary field deformation. And these geometrical interpretations have been extended in various directions after the initial work by Conti, Negro, and Tateo. And I think we'll hear a bit more of that in the same session as Daniele, if I remember correctly, at maybe 3:30 or something in Evangelos' talk. Okay, so for those who have not seen this before, I'll do a one-slide lightning review of this class of deformations. The idea of these auxiliary field deformations is to begin with a seed model, so an undeformed integrable model. And what one does is activate prescribed interactions by coupling the physical fields of the model to new fields, which I call V plus minus, that have algebraic equations of motion. So these are auxiliary fields, they're non-dynamical, but you engineer the couplings in a particular way so that it preserves the integrability of the seed. And in all of the cases, one could, in principle, put these auxiliary fields on shells, solve their algebraic equation of motion, which relates them to the physical fields, and then replace everywhere you see V plus minus with physical fields. And in general, this will give you some integrable deformation of the seed, which perturbs the original model with an infinite set of higher derivative terms. So there will be more and more irrelevant couplings turned on in general, but in a way which preserves integrability. So just a quick review of some of the facts that have been established about these deformations. So in addition to being lax integrable, the Maillet canonical structure is understood, so one can do the Maillet RS analysis and prove that the charges are in involution. These have been engineered from 4D Chern-Simons. There's applications to dimensionally reduced gravity in a work by Mattia Gestara and David Austin, who's here. And the set of models that you can apply these auxiliary field deformations to at the moment includes the principal chiral model with or without Wess-Amino term, the Yang-Baxter and bi-Yang-Baxter deformed PCM, symmetric and semi-symmetric space sigma models, and other Z and cosets. And as I mentioned before, another advantage of these deformations is that they play nicely with non-abelian T-duality, which we'll hear about in part of Daniele's talk. Now, the particular setting in the paper which this talk is based on is mostly the CPN or CPN-1 model. We shift the n by 1 because we want n to be the number of scalars in one presentation of this model. And the CPN-1 model has a coset realization. Now, one reason for caring about this model is that it shares many properties with 4D Yang-Mills. Many of these properties are at the quantum level. So for instance, this theory is asymptotically free but becomes strongly coupled in the IR. It involves classically massless complex scalars that develop a mass in the quantum theory, set by a scale lambda CPN-1, similar to lambda QCD. It exhibits confinement, and it has instanton solutions, much like 4D Yang-Mills. Now, unfortunately, most of those properties are quantum except for the instantons. I'll come back to the instanton solutions in a bit. But because I want to use integrability, and this model is classically integrable, but not believed to be quantum integrable except in particular cases like CP1 or if you couple to fermions in some way, the remainder of my discussion will be entirely classical. So I'm going to focus on aspects of classical deformations of models like this CPN-1. But in fact, because many of the results I'm going to discuss are somewhat more general and don't rely on the precise structure of CPN-1, I'm actually going to state most of my results for arbitrary symmetric coset models or symmetric space sigma models. And these, more generally, are theories of a field G from the worldsheet sigma into some coset, G mod H, where the Lie algebra frac G of big G splits in this orthogonal way. G0 is the Lie algebra of the H you're quotienting by, and G2 is the orthogonal complement. And these guys have to satisfy these particular commutator conditions which define what we mean by a symmetric coset as opposed to a generic coset. So any model of this form is one for which you can apply these auxiliary field deformations and for which the results of my talk will apply.
Sorry?
Yes.
Is there a reason why the grading jumps was 2 and not was 1?
Good. It's a very good question. Yeah, so I'm using notation which comes from an earlier paper where we did semi-symmetric space sigma models which have fermions. And in that case, we used the grading 0 and 2 for the bosons and 1 and 3 for the fermions. Okay. And we've kind of inherited that notation here. But there will be no fermions in this talk.
It's bosonic, right?
Yes, yeah, this is purely bosonic, so it's 0 and 2. That's right. Good. Okay, so that's the introduction. So the roadmap for the remainder of the talk is to geometrize these deformations. So I'll start by doing a quick review of how these deformations work in the symmetric space case, and then geometrize them as field-dependent metrics. Then I'll discuss this soliton surface interpretation, where you can view the deformations as a particular non-trivial choice of moving frame, is the term that we'll use, and then summarize and point out some future directions. But before going on, let me pause here and see if there's other questions about the motivation. No. Okay, very good. So let's jump in. So first, the review of how these deformations work for symmetric space sigma models, which, again, I don't need to tell you are interesting because they describe worldsheet sigma models for many target spaces of interest, like spheres or ADS spacetimes, except in special cases where you can use a PCM. So again, using the same notation, we have a symmetric coset valued field G from sigma into this coset. And we will decompose objects like the Lie algebra valued Maurer-Cartan form J is G inverse DG into their projections onto these two pieces of the Lie algebra. So I'll write J as its sum J0 plus J2, where each of the superscripts indicate which of the components that term sits in. And as you likely know, the first piece, the projection J0, plays a role a bit like a gauge field. So it's natural to define a covariant derivative. So this is, if you like, a J0 covariant derivative that acts on an object X in this way. And the field strength, which is built from J0, also in the usual manner. Okay, so in the undeformed case, of course, the symmetric space sigma model is integrable. Its Lagrangian can be written like this in terms of the projection J2. And varying leads to the equation of motion, which is the covariant conservation of this J2. So I'll use early Greek indices, alpha, beta, and so on for worldsheet indices. and usually use light cone, as I said, so alpha runs over plus and minus. And as we know, this equation of motion, along with the flatness condition coming from the Maurer-Cartan identity, is equivalent to the flatness of a lattice connection, which takes this form in terms of the projections of J and the spectral parameter Z. Now, there might be some unfamiliar signs here. Unfortunately, in this paper, to match with some of the soliton surface literature, we use a different convention for flatness where there's a minus in this third term. But if you like, you can go back to the usual conventions, which I usually use, where there's a plus, by just sending the lax to minus the lax everywhere. So just put an overall sign in the lax connection. Okay, so what about these deformations? So as I said, we'll couple to auxiliary fields in a prescribed way. In this setting, the auxiliary fields map the world sheet into G2, so this component in this orthogonal decomposition of frac G. And the Lagrangian for the auxiliary field symmetric space sigma model, for which I use this acronym, takes this form. Now, a few things have happened. First, the sign on the first term has flipped relative to the undeformed case. That's because when E equals 0, if I turn off this last term and integrate out the auxiliaries, these will contribute in a way that flips the sign back. So when E equals 0 and you integrate out V, this goes back to the undeformed model. So that's the sense in which this is a deformation. And it's a deformation parametrized by this function E. Besides the first term in the function E, there are just these very simple couplings between V and J and a VV term. Now, what about this E? What can E be? So E needs to be a Lorentz scalar to preserve Lorentz invariance, which is constructed only from auxiliary fields, and we call it the interaction function. Now, there's actually a huge amount of freedom in choosing this interaction function. Different choices lead to different integrable models. In the most general setting, this can depend on many variables, as long as each of those variables is what I call a chiral trace. So by chiral trace, I just mean a product of traces of V2, where within each of the traces, only V minus or V plus appears. So you could have something like trace V plus to the n, trace V minus to the n. This has all pluses here and all minuses here. And it's a Lorentz scalar because you have n pluses and n minuses. Or you can take these sort of mixed combinations where maybe you take a trace of 2V pluses and then cube it, so that's 6 pluses, and multiply by a trace with 3V minuses and square it, so that's again 6 minuses. And you can, as you can see, you can get more and more complicated combinations of chiral traces as long as the sums of all the pluses and minuses is 0. Now, for simplicity, even though you can consider this huge class of deformations, in most of this talk, I'm going to restrict to the simplest case, where E is an arbitrary function of just one variable, which is what this thing I call nu, trace V plus, trace V minus. And why do I restrict to that class? So we proved in the first paper that if you restrict to this class of deformations parametrized by a function of one variable, this class includes all deformations of the seed by arbitrary scalar functions of the energy momentum tensor. So this includes TT bar, root TT bar, combined TT and root T, root TT. You can pick any function of the two independent Lorentz scalars in general built from the stress tensor, say its trace and determinant, that you like. Of course, the trace vanishes in the undeformed theory, but once you deform by, say, TT bar, then the trace turns on. So all of those are within this class of models for particular choices of interaction function. Okay. Now, there's two equations of motion, one for the auxiliary and one for the physical field G. In this case, with an interaction function of one variable, the auxiliary field equation of motion looks like this. I use this dotted equality to indicate any equation that holds when the auxiliary fields are on shell. And you can see by eye, by moving the second and third term to the right and taking a commutator on the left with V minus plus, which kills this term, and only this term survives with a minus sign, you can see that you get this very nice constraint, that when the auxiliaries are on shell, the commutator of V with J is the same as the commutator of V with V. And that's the crucial underlying structure which actually leads to the integrability of this class of models. The second equation of motion for the physical field G can be written as this sort of on-shell conservation equation. So the first two, this is the equation of motion for G when the auxiliaries are off-shell. So this is the equation. But when the auxiliary field equation of motion is satisfied, you can see that these two terms cancel and this thing is 0. And here I've defined this curly frac J, which is just some combination of the regular J and the V, all projected onto G2. So you can think of this frac J as being the thing that's now covariantly conserved in the deformed models instead of the usual J. So to be clear, in this model, we now have two J's that are playing different roles. The usual Maurer-Cartan form J is now flat but not conserved, and the fancy frac J, at least J2, is conserved but not flat. Now, those commutator identities that I showed you imply, when you plug in the definition of this frac J, these two nice results. And all you need, I just want to emphasize that all you need to prove integrability of this entire class of models is these two commutator identities along with the flatness of the usual J and this conservation of the frac J. And the lax takes this form, again, with the minus signs to match the conventions I discussed before. So this is, I think, kind of elegant because all of the details of this interaction function E are now hidden. E doesn't explicitly appear anywhere here. It's hidden in the frac J through its dependence on V. So if someone handed me a particular interaction function E, then in principle, I could algebraically solve for the auxiliaries and integrate out to express this frac J, which depends on V, in terms of the physical J2. And then you would see derivatives of E appearing in various places. So you can do that in any special case that you're interested in. But for the purposes of proving sort of abstract properties about this class of models, it's much easier to hide all of the couplings in E and only discuss these implicit quantities that depend on E through V. Okay, so that's the review of how these auxiliary field deformations work for symmetric space models. Now I want to come to the new results. So as we said, there's a metric interpretation of the TT bar deformation, which is a special case of this class of models, in terms of doing a field-dependent diffeomorphism, which induces a metric that depends on the stress tensor. And the question I wanted to ask is whether that's more general. So is it true that the deformed equations of motion for all of these models can be recast as the undeformed equations of motion of the symmetric space sigma model with a field-dependent metric? So explicitly, the covariant conservation of here the regular J, the old J, but now where its index has been raised with some new metric H, or really H inverse, which is a function of J plus minus, or really J plus minus 2. This would generalize the TT bar case. Now you might ask, why am I discussing this at the level of equations of motion rather than at the level of the action? And the answer is that in the back of my mind, I'm thinking of something like what we saw in Masahito's talk, where this really should come at the action level from both minimally coupling the undeformed model to a metric, but also writing a metric sector for the action. So having a Lagrangian for the metric, with the property that if you solve the equations of motion for the metric and put it on shell, then the value of the metric on shell would reduce to the one that appears in this equation. So we haven't done that. I'll mention that in the conclusion as a future direction, but that's the intuition I have in the back of my mind, which is why I'm working at the equation of motion level. And I just want to emphasize that we saw that all you needed for integrability was the commutator identities, the flatness of little j, and the conservation of frac j. Coupling to a field-dependent metric modifies the conservation equation because you need to raise an index, but it does not modify the flatness at all because the flatness condition is metric independent. So in some sense, this has a chance of working because activating a field-dependent metric modifies the conservation, but does not affect the flatness. So we still need to check that activating one of these metrics preserves the commutator identities, which is the third ingredient. But at least this has a chance of working since it does not destroy the flatness. Okay. So the answer to the question is yes. There is an explicit field-dependent metric that you can write down for this entire class of models, and I'll spare you the algebra and just show you the answer. So for any interaction function that depends only on this one variable nu, there's an explicit expression for the field-dependent metric, which only depends on derivatives of the interaction function, the auxiliary fields, and this nu, which is a combination of traces of auxiliaries. So as a basic check, if you turn off the interaction function, set it to 0 or a constant, you can see that this vanishes, this vanishes, this vanishes, this vanishes, this is a 1, and this goes back to the flat light cone metric, which in our conventions is off diagonal with -2s. Another thing which is not so obvious about this metric is that if you compute the determinant of this thing, which has all sorts of auxiliary dependence when you take the products, it actually collapses to a constant, and in particular, the determinant is the same as the determinant of the flat metric, which in our conventions is -4. I call it a unit determinant field-dependent metric, even though its determinant is -4, just because it's the same as the flat metric eta. And that will be important. So that was not at all obvious that this determinant condition would pop out, but we'll see that this unit determinant condition is closely related to the commutator identities that are needed for integrability. Now, if you just explicitly compute, if you take the inverse metric and contract it with little j2, you'll find that it exactly reproduces the frac j2, which means that indeed the equation of motion, which is covariant conservation with respect to a field-dependent metric, the little j, is exactly the same as covariant conservation of the frac j when the auxiliaries are on shell. So all of this is consistent. It reproduces the equation of motion for the physical field in the deformed model. Now let me give you a little bit of a sense for why this is true and also explain a converse, which will illustrate why this determinant condition is important. So the converse of this statement, so we've proven that all of these auxiliary field models can be realized as coupling the undeformed theory to a unit determinant field-dependent metric. The converse is that if you hand me any field-dependent symmetric tensor, so express it as the inverse, but you could also express it for H, and if that thing has this determinant property, where its determinant is a constant and matches that of eta, then the theory with the equation of motion here, this covariant conservation with respect to this field-dependent object, which I interpret as a metric, is integrable. That's somewhat surprising. So let me just, in a very naive way, show you why this is true. Again, taking these conventions where the off-diagonal light cone metric components are -2, I'll just lower an index on this H inverse to define this object R, so that frac j is now just the matrix multiplication of R with the old little j. In components, H inverse looks like this. So when I multiply with an eta, it just mixes up the components. So now R has equal diagonal entries and unequal off-diagonal entries. For simplicity, I'll call those A, B, and C, so that R just looks like this. R is an SL2 matrix because it has unit determinant, since by construction, if I take the determinant of this thing and assume this, then the determinant is 1. But it's not a generic SL2 matrix because the diagonal entries are equal. And all of these A, B, C depend on fields. So these are functions of fields and therefore functions of spacetime. But I've suppressed them. Now, why does this bias anything? If you just write out the components of this matrix equation relating the frac j and little j, it just looks like this, that the frac j components are sums of components of the little j's, and then you just compute commutators. So you put in these expressions in the commutator of frac j's and collect the a squared and bc terms coming from expanding the commutator and use the determinant condition and see that that commutator reduces to the old one. Likewise, if you take the commutators that are mixed with the frac j and a little j, you just get the a term contributing, and it's the commutator of the little j's. Same thing happens if you go in the opposite direction, j plus with frac j minus, it's the same thing. And therefore, these two commutators agree precisely because the diagonal entries of this matrix are equal. And as I said before, those commutator identities are sufficient for integrability once we have the conservation of frac j and the flatness of little j.
Wait, sorry, are you assuming that the components of R comes out of the commutator?
The component, oh yeah, so good. The components, yes, no, the one unstated assumption was that the components of the matrix R are all essentially traced. So they trivial commutators, right? So they're numbers, well, they're functions of fields, but they're functions of fields that have traces, so there's no more commutators. That's right. Good. Any other questions about this? I'm a very simple-minded person, so I need to make the algebra sufficiently pedestrian that even I can understand it. But other questions about this this simple calculation? Good. Okay. So you might ask, what is this useful for? I think it's, first of all, just nice to have different interpretations of classes of deformations like this, and the geometrical one is very nice because it connects to the TT-bar discussion. But you can actually use this to give a very satisfying interpretation for another fact about these deformations, which now connects back to the instantons. So I mentioned at the beginning that in particular, the CPN-1 model shares many properties with 4D Yang-Mills. 4D Yang-Mills has instanton solutions, effectively because the third homotopy group pi3 of G is the integer Z for any simple compact Lie group G. So you can have winding around a large sphere for one of these instanton solutions. Similarly, pi2 of CPN-1 is Z. So you have analogous winding type solutions of the CPN-1 model. A feature of all of these instanton solutions is that they have vanishing stress tensors. So in the undeformed theory where the only components are T plus plus minus minus, all of those vanish for these instantons. And you might ask what happens to those instantons when you deform. If you couple two auxiliaries in one of these ways, do the instanton solutions remain solutions? Are they no longer solutions? Or do they deform in some interesting way? And in the paper, we prove in two different ways that, in fact, all of the instanton solutions are undeformed. By which I mean, if you have any instanton solution, more generally than CPN, of any symmetric space sigma model, which is one for which the stress tensor components vanish, then if you evaluate this field-dependent metric that we saw before on those solutions, then it collapses to the usual flat metric eta. And that's sufficient to conclude that all of those instanton solutions remain solutions of the deformed equations of motion, because in order to test whether something is a solution of the deformed equations of motion, all you do is take that field configuration, evaluate H, and then ask whether this equation is true. So if H is eta, and these instanton solutions solve the undeformed equations of motion, which is exactly this with H equals eta, then it follows that they also solve the deformed equations of motion and the instantons are still there. So I mentioned we proved this in two ways. One is a brute force way that does not involve any geometrical interpretation. So if you don't like the metrics at all, you can refer to that proof in the paper. I'll give you a very simple one-slide proof sketch for why this holds using the metric interpretation. It's actually quite basic. So what we do is take this auxiliary field equation of motion, which I showed you several slides ago, that just looks like this. You can solve for J, so move everything else to the right side and then square it. So you'll have two J's and then take a trace. So when you square and trace that equation of motion, you get something like this. Everything I'm going to do is with the auxiliaries on shell. So trace of two J's is a product of this guy and this big thing. Now we're looking at instanton solutions of the Steve model. So those are ones for which the stress tensor vanishes. That happens if and only if trace of JJ is 0. So that means the right side has to vanish. And then there's two possibilities. Either the first factor vanishes or this big thing vanishes. In the second case, if this whole thing were 0, this is a quadratic equation for the derivative E prime. You would solve that quadratic equation and express E prime in terms of this thing, which is the variable nu I introduced before, and this thing, but that's bad because the second variable, this trace V plus V minus, this is not a chiral trace. Remember, chiral traces are the only ones that E can depend on, and chiral traces mean only all pluses or all minuses appear within each trace, and this one has a plus and a minus. So if you could solve for E prime, and therefore E, in terms of that variable, it would be a contradiction, because E cannot depend on non-chiral traces, and therefore we reject that possibility and conclude that the first equation holds. That for instanton solutions, this trace VV must vanish. And if trace VV vanishes, we can look at the expression for the metric. If trace VV vanishes, then this is 0, and nu is 0. So indeed, the whole thing collapses back down to eta. Now, this is kind of intuitive in some sense, because I told you that at least for interaction functions E of nu, all of these models correspond to deformations of the undeformed theory by functions of the stress tensor. So morally, what we're saying is that if you take a solution for which the stress tensor vanishes and deform the Lagrangian by some function of the stress tensor, then it remains a solution, which is intuitive because the stress tensor is 0 on that solution. But that set of words I just said, although intuitive, is not really a proof, because when the Lagrangian is an off-shell statement, so when you, an off-shell object, so when you deform the Lagrangian by a function of stress tensor, it's not immediately obvious that for field configurations for which the stress tensor vanishes, that you don't get additional contributions from the variation of the stress tensor. It could be possible that the stress tensor is zero, but its variation is non-zero, and it spoils the solution of the equations of motion. The statement of this theorem is just that that does not happen, that all of these instantons remain solutions in all of these deformed theories. Okay, so that's all for the metric piece. Let me pause here again and see if there are questions about that. Yeah.
I mean, I have a question. Is there a physical interpretation of this metric which you get, which depends on the field? I mean, is it some pullback from the target space or so? But in this case, it would depend on the field, right?
Yes, good.
Because in principle, it depends on your group elements G, right? Which are the target space coordinates in the signal model.
Yes, that's right. I don't know of such an interpretation, but indeed, if you put all these auxiliaries on shell, this would be a metric, a worldsheet metric, which depends on all of the G's through the J plus minus. And in principle, I guess you could try to engineer an exotic target space metric, which would reproduce that when you pull it back. But we didn't attempt to do that.
These also depend on like string worldsheet derivatives of the target space fields, right?
Yes, it depends on plus and minus derivatives of G, because all of these will depend on J plus minus, which itself has derivatives.
It doesn't.
So it's not really a pullback then, right?
Yeah.
So it's much more complicated.
Yeah.
But is there any interpretation in string theory, or not really, right?
It seems like you're just moving out of the class of signal models.
Yeah.
It could be. I mean, I thought about this a bit and did some reading about this rather niche topic of Finsler metrics. I don't know if you've heard of Finsler metrics, but there's a generalization of a Riemannian metric where the metric components don't only depend on the coordinates, but also have some dependence on the tangent vectors themselves. So now it's not a bilinear form anymore. It's not G mu nu dx nu, but some more complicated dependence on tangent vectors. And there are some papers claiming that you can get these Finsler metrics in exotic string theory constructions, which I don't really understand. So at the level of wild speculation, since indeed these metrics would not be pullbacks of conventional ones because they involve derivatives of fields, it might be that they sit within this more exotic class of non-Riemannian metrics. But I was never able to make anything in that direction precise.
So there's a singularity of that metric.
Aha, good, someone caught it. Okay, so I mentioned this later. I should have mentioned it here, but I intentionally left it to see if anyone would ask about it, and you passed the test, so very good. Let me just jump to one. I will highlight just one statement. So in the next part of the talk, the same denominator will appear, and you could have asked, is this always well defined? What happens when the denominator blows up? And as it turns out, that denominator vanishes only for the interaction function E of nu is plus or minus square root of nu. And that interaction function corresponds to the root TT deformation of the seed in the limit where you take the deformation parameter to plus or minus infinity. So in that sense, it's a quite singular limit. These infinite deformation parameter limits of root TT type deformations have also been studied by Dima Sorokin and others in the context of 4D modmax theories. And those limits are very weird. They lead to theories that they have a lot of bizarre properties. So all I'll say is that I'm going to exclude those sort of pathological infinite deformation parameter limits from consideration because they're quite bizarre. And if you rule out that case, then the denominator is always finite, and then you're safe. Very good. People are awake. All right. Other questions or comments before the solid tensor? Okay, I have 14 minutes, so in good shape. Okay, so I knew nothing about these soliton surfaces before starting this project. I mean, in this audience, perhaps this is obvious to everyone, but if you'll permit me just a couple of slides of review, since I find it somewhat interesting. This goes under the subject of these so-called immersion methods, where immersion refers to an immersed surface. And the nice thing about this topic is that it allows you to recast many features of 2D integrable models in terms of geometrical statements about these immersed surfaces, which are often called soliton surfaces. Now, there are several different ways of doing these immersions. There's some Gelfand immersion method, there's various other ones, But the one that we used is what I'll call the SimTOEFL immersion following these two papers, which introduced some of this machinery. And in many cases, these immersion methods coincide, so the resulting surfaces are the same, but I'm just going to discuss this particular method. So what is this? It's a quite general procedure. If you have a 2D integrable model with a lax connection that's valued in a Lie algebra, like the one that we're discussing, you define this auxiliary object phi, which is valued in the associated Lie group, by solving what's called the linear spectral problem. So the lax acting on the field phi is the derivative of this field phi. Both of these depend both on the space-time coordinates, or sorry, the worldsheet coordinates x plus minus, and the spectral parameter z. And once you've solved that and found phi, you define a function r using this SimTOEFL formula, which is r is phi inverse times the spectral parameter derivative of phi. So what does this do? This gives you a family of surfaces labeled by different z's, and for each fixed z, this is one map from the 2D worldsheet into the Lie algebra frac G. This is why it's called an immersion or an immersed surface. So you have the worldsheet is mapped into the Lie algebra in some way. So you might ask, why does this have anything to do with integrability at all? There's a simple way to see it, which is that the solution to this equation, which defines the surface, is consistent if the theory is integrable. And an easy way to see why that's the case is to compute the tangent vectors to the surface, which I call r plus minus. They're just the plus minus derivatives of r. A one-line calculation you can do shows that that takes this form in terms of z derivatives of the lax. You can then differentiate again to find the second derivatives, this d plus minus r minus plus, and that takes this form. And on a smooth surface, it had better be that the mixed second derivatives agree. So if I take the second derivative plus then minus the second derivative minus then plus, it had better vanish. And if you just plug this in and do some algebra, you'll find that that difference takes the form of some conjugation by phi's and then a z derivative of the flatness condition of the lax in my conventions with this minus. So this doesn't actually imply integrability. The implication goes in one direction, because if the lax is flat for every value of the spectral parameter, then of course its z derivative vanishes. So integrability implies the consistency of the surface, but this particular consistency condition is somewhat weaker. If the curvature of the lax were constant and independent of z, it would also hold. But this is one way of seeing why integrability is sufficient for this surface to be well-defined and smooth.
If you just use R and just let the linear system be consistent, you get the max up. Right?
Yes, yeah, you could also phrase it that way.
The extra Z just comes because you defined R as the Z derivative of something.
Yes, that's right. Yes,
so you do need the lax.
Yes, so for
you define phi.
That's right. Yeah. So a different way of saying it is that, yes, so this is one consistency condition, but not all of them. There are other consistency conditions. And you could ask, when are all of the consistency conditions satisfied? So when is this linear system well-defined? For all of them to be satisfied, you do need flatness of the lax on the nose and not just the z derivative. A different way of saying this is that for a general immersion, you need to satisfy three equations: the Gauss equation, the Kadasi minority equation, and the Ricci equation. And for all of those equations to be satisfied for this surface, not just equality of mixed second derivatives, you actually precisely need flatness of the lax. And that's just an equivalent way of saying that the linear system is consistent. Good. Other questions?
The initial equation, you can multiply phi on the left by, on the right by an arbitrary function of z.
In this equation.
Another solution. Would it correspond to the gauge transformation?
Good. If you multiply by
A function of z alone.
Function of z on either side, indeed, since good. Yes, I think indeed, because that would go right through this plus minus derivative, and that would correspond to some redefinition of phi, indeed.
But it would change r.
Yes, but it would change r. Good. Yeah, I suspect this is some gauge transformation or reparameterization of the surface, because this is not unique. You can parameterize the surface in many ways, and I suspect that gives you some equivalent parameterization or some gauge type transformation or something.
You fixed that by fixing some initial condition of having x
Ah, good, okay, yes, because then that the initial condition would give you, yeah, would pin that down. Very good. Okay, other comments? Okay. Okay, so why is this nice? So I advertised that this machinery allows you to convert integrability statements to geometrical statements. One way of seeing that is to compute the metric tensor on the soliton surface, which is the pullback of the bilinear pairing of these tangents, the r plus minus, if you like. So I'll always use the trace as my pairing. So this metric on the soliton surface is built out of derivatives of the lax connection in some way. And as a simple example, if you evaluate this for the PCM with, again, my minus sign conventions, you find that the plus plus minus minus components of the lax are proportional to the stress tensor, and these off-diagonal plus minus components are proportional to the Lagrangian. So this suggests that if I do a stress tensor deformation of one of these theories, or equivalently an auxiliary field deformation with E depending on nu, since that deforms the Lagrangian by a function of the stress tensor, it should be that this also deforms the metric on the soliton surface in a particular prescribed way, which preserves integrability. And we'll see that that's true. So it does deform the metric on the soliton surface in a non-trivial way that's quite reminiscent of the field-dependent metric, but in a way that all of these consistency conditions are preserved. I'll just mention one other nice fact about these soliton surfaces. So you can also interpret the monodromy matrix, which gives you the tower of conserved charges in the model, in terms of periods of the soliton surface. So say on a cylinder where you can have a period around the cycle, computing that period, which is integrating the R derivative with respect to sigma, you can do a computation using properties of path-ordered exponentials, and you find that that's related to this sort of logarithmic derivative of the monodromy matrix. So this geometrical period data directly encodes some facts about the generating function of conserved charges in the model. Okay, this is all undeformed. So now we ask what happens when you couple to the auxiliaries.
Kristen?
Yes.
Maybe you already mentioned this, but I missed it. What's the key motivation for, like, you've given the construction of these soliton surfaces and you can then define a metric on this surface. Why are we, what's the kind of key motivation for this construction?
Good. So broadly, it's within the purview of just attempting to geometrize these deformations. So one way of geometrizing it is through the field-dependent metric directly on the worldsheet. A second way that you might attempt to geometrize it is by studying these soliton surfaces because they encode a lot of the physics of the model, like the charges and dynamical things like the stress tensor, and just asking what is the effect on this geometrical object, the soliton surface, when you do the deformation. So I do concede it seems like a slightly different motivation since it's not directly related to the first part of the talk, but a different motivation if you come from a more mathematical / geometrical background might be to say, well, there are many interesting deformations of, say, Riemannian manifolds like Ricci flow, which are of interest for various reasons. And you might ask whether the auxiliary field deformations of these soliton surfaces, which, although we'll see that they look quite non-trivial, they still preserve all of these consistency conditions because they preserve integrability. You might ask whether, forgetting about the sigma model at all, whether studying this class of deformations of surfaces is of interest in its own right. That's another way you might motivate this. Okay. All right, so in the deformed case, again, restricting to this interaction function of one variable, in the paper, we do the computation. So we repeat the steps that led to this in the undeformed case. And the simplest way to express the deformed metric on the soliton surface is to express everything purely in terms of E and its derivatives and the auxiliaries. So when you do that, you find these reasonably compact expressions that fit on one line each. They all reduce as well to the undeformed case when you set the interaction function to a constant or to 0, but they're still somewhat involved. So in the paper, what we do to simplify things is to restrict to the case of CQ1, which is a 2-sphere. In that case, the normal bundle is rank 1, so things simplify a bit. You can use kind of the usual classical differential geometry of surfaces and define cross products and things like that. And for this particular case, we compute the mean curvature and Gauss curvature of the surface in this deformed case. And at least to me, I found it somewhat surprising that the Gauss curvature is completely undeformed. So the K has no dependence whatsoever on auxiliaries or on the deformation at all. It just reduces to this spectral parameter dependent quantity that agrees with the undeformed theory. The mean curvature depends on V. So this has field dependence. And in particular, this mod I'm using in the bottom is sort of compact notation where the mod squared is the trace of the commutator all squared. So this mod is the square root of the trace of the commutator squared. So this thing changes. Okay, so now you might ask, is there an interpretation of this procedure you've done to the surface analogous to the field-dependent metric that we had in the previous part of the talk? And the answer is yes. So we can realize this as a particular choice of moving frame, it's the term that I used before. And it's simplest to state that transformation by going from the usual tangents r plus minus to what I'm calling these fixed body tangents, p plus minus. They're related just by taking an adjoint by phi to strip off the phi inverse and phi on the r's. And that means they're just z derivatives of the lax. Now by add invariance, this defines the same metric, of course, because I'm just doing some adds. So the R alpha, R beta pairing is the same as the T alpha, T beta pairing. So for questions involving the metric on the soliton surface, the T's are just as good as the R's. So what does the deformation do to these fixed body tangents? Well, it's actually pretty straightforward to compute. These tangents in the undeformed symmetric space sigma model just take these forms in terms of J2, J plus 2, and J minus 2. And after the deformation, they take this modified form involving the frac J's. So there's both frac J's and the little j's in the expressions for the new tangents. And much like the field-dependent metric picture, these deformed and undeformed tangents are just related by a funny pseudo-linear transformation by this lambda tilde. So you multiply the undeformed tangents on the soliton surface by this matrix lambda tilde and get the deformed ones. Why am I saying pseudo-linear transformation? Well, it's a matrix, but the entries of this matrix depend on the fields V. So the V plus and V minus appear, and the nu also appears. There's also derivatives of the interaction function. But when you go on shell, you replace the auxiliary fields with the J's using their equations of motion. Recall that the J's are themselves related to these tangents in the undeformed theory. So this is a sort of bizarre transformation since you're multiplying by a matrix where the entries in the matrix depend. Yes. Oh, I just finished it. Okay, I'm over time. Good. Okay, so good. Okay. Okay, so the punchline is that good. Because of this transformation, the deformed and undeformed soliton surface metrics are related in a way that looks much like introducing a frame, but it's a sort of bizarre frame because the entries themselves depend on the undeformed tangent vectors. So it's somewhat surprising that you can do this transformation and preserve the consistency conditions for the surface, but you do because of integrability of this family of deformations. Okay, so just to wrap up, what did we do? We studied these auxiliary field deformations for symmetric space models like CPN-1. We showed that any stress tensor deformation can be interpreted as a field-dependent metric. We showed that instanton solutions are undeformed. We studied geometrical properties of the soliton surface like curvatures. And I discussed this choice of moving frame on the soliton surface that enacts the deformation. And there's many future directions that I think are interesting. As I alluded to, you could try to realize these field-dependent metrics as coupling to a gravitational sector, a bit like what one can do in the TT case, and we heard a bit about from Masahito. You could try to study quantum properties. You can study the higher spin deformations that are not deformations just by functions of stress tensor, but higher spin charges. And you could try to push further the realization in 4D transiments that appeared in this paper. I think progress in any of those directions would be very interesting and expand our knowledge of these integrable deformations and would be very cool to think more about. So thank you for your attention.
Questions? There were quite a few in the talk already, but any more? Yeah, Lisa?
I was just wondering if you could show this transformation that you 2 slides ago.
Good. This funny linear transformation thing. Good.
Yeah.
Yes.
So,
Good.
so here's a new
And it has the same denominator as before in the field dependent metric.
No, it was just, I don't know if it's a question or a comment, but it smells a lot like the Darwin vacuum transformation, which
Yes.
obviously, and I mean, it's got a typical structure of such things. So I'm wondering if you're rephrasing the deformations in terms of this well-established transformations in the silicon surface language. That has a good structure.
Yes. I believe you're right. I'll make a somewhat embarrassing confession. I did not know what these transformations were, but after putting this paper out, I uploaded the paper into ChatGPT and asked it, do you have any comments about this paper? And it said, your moving frame is much like a Darboux-Backlund transformation. So
Just as good or as bad as
I hope that it's not a hallucination, but I think it's.
I think it's probably right. Yeah, it feels like it's the right frame to interpret.
Yes, I think we now have two experts at very different levels that agree with this analogy. So I think it would be interesting to investigate, but I know nothing about the subject.
At least you waited till after you wrote the paper.
I didn't want to bias myself, I would say. ChatGPT was also quite complimentary. It said that it's a very nice paper with beautiful geometric interpretations, blah, blah, blah. And I disregarded the sort of.
What did the referee say?
That we're still waiting, but we'll see.
Any more? Yeah,
Yeah, so for the original TP bar deformation component, the determinant of the stress tensor, we have some idea how to define it at the quantum level. Can you see anything here that deformation would be special, or is there any hint? Or do you expect to be able to say something about these other more general deformations?
It's a good question. We've been trying to find additional conditions you might impose in order to have good quantum properties for this class of models. For TT bar, this is one motivation for realizing the field-dependent metric via a gravitational sector, because in the TT bar case, that specific gravitational action that you write down is quite special, and it actually allows you to do the path integral explicitly and find quantum properties like the torus partition function, which satisfies the diffusion equation. You can get the spectrum, which satisfies an implicit Burger's equation. So from what I've presented so far, it's not immediate to do that analysis and identify which subclass of these deformations have good quantum properties. But I think with a bit more pushing, maybe finding the metric sector or asking about whether the conserved charges remained conserved at the quantum level or some analysis like that, you might be able to single out a subclass of good quantum deformations. It's very interesting.
thank you. So we don't want to eat too much into our coffee time. So maybe we'll leave here the questions. We can continue with coffee. We come back at 11:10 for Vincent, and we thank you again.